Okay, so in this video, we are going to introduce the topic of hypothesis testing, the basic ideas, basic concepts, and the basic terminology. I will not write out definitions completely because you have a summary PDF document that you can find on the course website. So let's look at what is the basic idea of hypothesis testing, right? There may be something you believe to be true, and the idea is, well, how do you support your claim? You would gather numerical evidence, so you would gather data, and then you would see whether or not the gathered data supports your claim, right? You have to justify making the claim, and the justification comes from the data that you have gathered. So there are two types of hypotheses. The first one is called the null hypothesis, and we'll denote this by H0. The other is called the alternate hypothesis, denoted by H1. Let's look now at just the null hypothesis. So we will formulate the null hypothesis, and this will be the hypothesis of no change, or if you prefer, representing the status quo. So there are two options. Either H0, the null hypothesis, or H0 is true, or H0 is false. As I have just said, this will be the hypothesis of no change, or the status quo hypothesis. And then the question is, we will formulate H0, and then formulate H1, the alternate hypothesis, but then we'll make a decision. We will decide to either accept H0 or reject it. So either we accept H0, so we accept the hypothesis of no change, the status quo hypothesis, or we will reject the status quo hypothesis. Okay, so look at this case. What if we accept H0 and H0 is true? Then we are correct. So great. What if we reject H0 and H0 is false? Then we were right to reject it, so we are also correct. We are also right. But if you notice the other two cases, we are actually making an error, right? If H0 is true and we decide to reject it, this is an error, and this is a so-called type 1 error. I'm not a big fan of the terminology type 1 error. I prefer, you'll see why in a second, the term false positive, which is much more intuitive. Think of what this says. False means you were wrong, and the adjective positive, and you'll see here negative, is about the possibility of a change. So if you reject H0, and H0 being the hypothesis of the status quo of no change, by rejecting H0, you say that there is a change. So you were positive about there being a change, and we were false about saying that. So when you have a false positive, you were wrong about saying that there actually was a change. Therefore, you rejected H0, therefore the positive presence of a change, but you were wrong, and so H0 was actually true. Well, the other type of error, if you accept H0, but H0 is false, you're also making an error. This is a type 2 error, which again doesn't really say much. But this is a false negative now. False again because we're wrong. Negative because we were saying that there was an absence of change. If we accept H0, H0 is the hypothesis of no change, or the status quo hypothesis. We accept that there is no change. But if H0 is false, then there is a change, So we were wrong, false, about there being no change. There was indeed a change. So this is more intuitive. So false positive, you were wrong about saying there was a change. So you were wrong about rejecting H naught when H naught was true. False negative, you were wrong about saying that there was an absence of change. Therefore, you were wrong to accept H naught when H naught was false. Okay, now, and this is really the philosophical issue, which error do we try to minimize the probability of? And this is really a philosophical decision, but we will choose to minimize a false positive. We will choose to minimize the probability of a false positive simply because the philosophy of our society is that we favor the status quo. So we don't want to say there is a change unless we're unless the evidence for change is really strong. So we'll try and minimize this type of error as much as possible. Okay. The question is, though, what is our threshold for the probability of a false positive? We will never know for sure whether we are right about H naught or wrong. So there's always be a possibility of us being wrong. And we call the probability of a false positive alpha. So alpha, this is the Greek letter A, is the so-called significance level. But this really is our threshold for the probability that we are willing to make a false positive. This is the probability of a false positive. So always think of alpha being a threshold. With what probability are you willing to make an error? Are you willing to actually be wrong? So usually, alpha would be fairly small. It might be anywhere from 1 to around 5%. So now let's look at H1, the so-called hypothesis of change or the alternate hypothesis, and see what types of tests we may have and how we use alpha, our threshold, the probability of a false positive that we are willing to make to decide if we accept H0 or reject H0 and therefore accept H1 instead of H0. We will always be giving the status quo the benefit of the doubt. So we will always be assuming that H0 is true. And we will formulate a counter hypothesis, the so-called alternate hypothesis H1. And I'll write here what H1 could be for a test about the mean of a population, but it's the same idea if you were testing for the standard deviation or a proportion. So usually in H0, for a mean, you'll say the mean is equal to some value. So you say it's been established with previous data that the true mean of a population equals a given value. Think of this value as the status quo value. Then you come along and you say, I no longer believe that this is true, and you can formulate a counter hypothesis, a hypothesis of change that goes against the status quo value of the mean. And there are three types of hypotheses that you can make. The first one, you can say mu is actually less than the status quo value. And this will be called a left tail test because we're seeing less than. Or you could say I believe that the mean is bigger than the status quo value. So mu is bigger than the status quo value. And now you're saying mu is bigger than this value. So we have a right tail test. Or the other option is you're not as affirmative, and you simply say that you believe mu to be different than the status quo value. So a slightly weaker statement. And this is a so-called two-tail test. Two-tail because if you say mu is not the status quo value, well, either mu is less than the value or bigger than the value, and so we are going to reject the two tails of our distribution. Here we are going to reject the right tail of our distribution, and here we are going to reject the left tail of our distribution. And this is how we will actually factor our significance level with our type of test. And remember that alpha is our threshold. With what probability are we willing to make a false positive? And we need just one other definition, and that is the p-value. When we want to test this hypothesis in H0 and H1, what we do is, again, we gather data, and we will find an observed value of a statistic. And then we're going to ask, okay, under the assumption of H0 being true, is what we have observed a likely event or an unlikely event? And the probability of observing what we have observed, or more extreme, is the so-called p-value. So the p-value, again, this is found after you collect the data, you compute your observed statistic, and then you ask, what is the probability of observing a value equal to or more extreme than the observed value from our sample? And that's the p-value. So the probability of observing a value of our statistic, so a value of the statistic, as extreme or more extreme than the one observed from our sample. Simply put, we will be assuming H0 is true, so giving the status quo hypothesis the benefit of the doubt. We will take a sample, a random sample, we will compute an observed value of a test statistic, and then we're simply going to ask, what is the probability of observing something as extreme or more than the one we have just observed? And if this is really, really likely, well, that is evidence for H0. But if what we have observed is really unlikely, that is evidence against H0. Let's see now how this factors in with the significance level, our threshold, our type of test, and the p-value. So suppose that we have a test for the mean, and say we will either in the case use a t or a z distribution. Suppose we use a t distribution, and so we draw. So our hypothesis was, say in this case, mu was less than the actual status quo value. So you would draw your t distribution. And so here we're looking for values that are less than the actual status quo value. So we will actually reject the lower alpha percent of our distribution, right? Alpha is the probability of making a false positive, therefore assuming H0 is true, but rejecting it. So we would reject the left tail of our distribution, where the threshold is alpha, our significance level. And again, alpha will range between 1 and 5%. So if you think of it, and here you'll see there are two approaches. There's the so-called p-value approach, and then there is the rejection region approach. They are equivalent. In this course, though, we will use the second approach, the rejection region approach, simply because it will be easier to work with our distribution tables. But let's see. So we assume that h naught is true. And then you say, well, okay, if we have a left tail test, the probability of observing a t-score inside this interval is alpha percent or less. And because alpha is small, this is really, really, really unlikely. So this would be the so-called rejection region. And so if you observed a value of your statistic inside of this region, you say this is too unlikely. You say, well, wait a minute. We were assuming h naught, and we have observed a value of our t statistic that is in this region, and this is really unlikely. Therefore, we have evidence against h naught, and we would end up rejecting h naught. That would be the rejection region approach. If you use the p-value approach, well, if you think of it, the p-value is the probability that you observed a value as extreme or more extreme than the one you have just observed under the assumption of h naught, the status quo hypothesis. So think about it this way. If your p-value is large, then you're saying that what you have observed was fairly likely, so that's evidence for h naught, it supports it. But if your p-value is really small, then it doesn't look so good, because you see, I assumed h naught was true, and from that assumption, I observed a value of my t statistic that is with a really small probability. And so that's too unlikely, so that's evidence against h naught, and you would reject it. But the question is, well, how small is too small? And that again is our significance level, our threshold. So we're saying if what we have observed as a probability less than our significance level, we're saying this is too unlikely, and we would reject h naught. On the other hand, if our p-value, the probability of observing something as extreme or more than we have observed, is at least alpha or bigger, then you say it's not that unlikely, and we would simply accept h naught. And that is the p-value approach. And again, an equivalent approach is the rejection region approach. Now this value of t will depend on the degrees of freedom for your t distribution, which is n minus 1, and alpha. But suppose I call this t here, then you'd have a rejection region from negative infinity to t. And again, this region would contain the smaller alpha percent of values, and these are really unlikely because alpha may be ranging from 1 to 5%. So the odds of observing a value inside this interval is really small. So here we assume we had a test for the mean, so we would observe a value for a t-score, and I'll write this as t subscript OBS. This is the observed value of the t-score that we obtained from our sample. And there are two possibilities. Either our t-score falls inside the interval, the rejection region, or our observed t-score falls outside of R, so it does not belong to R. Then you ask, well, in each case, what is our conclusion? Well, if you think about it, R contains, in this case, since we had a left tail test, the smaller alpha percent of values. Alpha was our threshold, so since alpha is very small, a value falling inside of this interval is really unlikely. If you think of it, if you ask what is the probability that we observe the t-score inside this interval, the answer is alpha% or smaller. So that's really unlikely. So therefore, this is evidence against H0. So if you ever observed a value of your statistic inside of the rejection region, it is too unlikely, evidence against H0, and so we reject H0. On the other hand, if your observed value of the statistic is outside of the rejection region, then it's not that unlikely, and so you say, well, that's evidence for H0, and so you accept it. And that's basically it. So you see, if there's anything unclear, when you go through the other 3 videos, hopefully this will become clearer. But that would be for a left-tailed test, and now you can imagine if you had a right-tailed test, well, instead of rejecting the lower alpha% of the values, you would reject the upper alpha% of the values. And this is the one last comment I want to make here, where you have to be careful. What if you have a two-tailed test? You won't be rejecting alpha and alpha for the left tail and the right tail. Alpha is the percentage of values you reject in total. So if you ever have a two-tailed test with an alpha level of significance, you have to reject a total of alpha% values, so you would reject alpha over 2 of the right tail and alpha over 2 of the left tail. So in total, you're rejecting alpha% of the more extreme values. And that is the idea of hypothesis testing. But as I've said, if there's anything unclear, make sure you look over the summary PDF document on the course website. And as you go through the next 3 videos, hopefully these ideas will become clearer.